just record it.
So things like number 1 has a hydrogen donor and hydrogen acceptors, so they could potentially hydrogen bond.
So as soon as we see water solubility, and in particular the solubility, what we should be focusing on is the term like dissolves like, which I don't like. See if I can use like again. Like forces dissolve like forces, which we mentioned in class. Okay, well, if we're doing like forces, then what we need is, what are the forces? Okay, so what are the forces found in water? Based on our structure, we have hydrogen bonding. So what is a similar force to hydrogen bonding? True, but hydrogen bonding is even more similar to hydrogen bonding than dipole-dipole. I mean, you can repeat, there's no problem with that. So we would go through and look for situations where we could hydrogen bond. Well, anywhere I have an oxygen and a hydrogen, I can hydrogen bond. So those are all hydrogen bonding sites. 3 has no hydrogen bonding sites, which means what intermolecular force am I likely going to see in 3? London dispersion forces. Well, London dispersion forces are incredibly different than hydrogen bonding, which would suggest, as far as solubility goes, and we would then go through and say least soluble, 1, 2, 3. Okay, we know that's our extreme. Deciding between the other 2, well, we've got both of them having hydrogen bonding interactions. Okay, so how do we decide between those 2, which one should be better? This one has more hydrogen bonding options. So what does that mean?
It's
more likely to interact with water. Okay. We've got general notes now all over it. I would probably be able to discern what you were trying to say and potentially give you full credit. Okay. You should probably put it into a sentence explaining your reasoning. Okay. 3 is the least soluble because it is the most different as far as intermolecular forces. 1 is more soluble than 2 because 1 has more hydrogen bonding.
You could say 2 has a long non-polar chain.
Okay. If you chose to avoid the hydrogen bonding aspect, you could look at the different aspect. 2 has a long London dispersion force chain, which is going to avoid water, which will likely make it more difficult to dissolve in water. Okay. Both tactics would work fine. Kind of make sense?
So
okay, before we continue, it asks to explain why. Why do we need a suitable pKa?
Because if you pick a similar or different in the wrong direction, it's not going to buffer anything.
Okay, well, why is the buffering a big deal? So we want, okay, a good buffer. Okay, but that's now saying what the question asked.
you want to find where the pH, so depending on the system that you're looking at, you want to find a pH that's relevant to the system. Because when you had multiple buffers or multiple pKa's, if we're looking at 7 and there's a pKa of 2 and a pKa of 6, we're more interested in a pKa 6 buffer because that's in the range that we want.
Okay, but why? You're right. Okay, so a good buffer, we've now spun in and brought in a little bit more information and said we need the pH that's relevant to the system. Why do I care that the pH is relevant to the system?
Because if you want to keep the pKa at, say, 4,
Well, you'd be keeping the pH at 4, so you'd pick a buffer that had a pKa about 4. But why?
So you can mimic the system in which you would find it so that you can see how it would function in that system.
Yes, you're mimicking, but why do you need to mimic that system? Why would the protein care? Why does it need to be at a pH of 4?
Oh, I see where you're getting from. So work within a given pH range, so you want to be able to stay within
Yes.
that range.
The protein only works in a given pH range. Why? You're right. Okay, everything you've said is right, but it's now, why does it only work in that range?
Because that's the only time the acid is even there, existing. Because in the other parts of the titration curve, it doesn't, that specific thing isn't
What makes a protein?
amino acids.
So here's an amino acid, right?
Is it the whole, you have like 2 acidic functional groups that?
We have an amino acid here, and you might be starting to answer my question, Jimmy, so we'll hold off just a second on what you're going through. There's our amino acid. What pH is this?
Very low.
Very low. We're in the fully protonated state. Okay, so there are a couple answers to that. You can dodge the pH question by saying very acidic. Okay, and the only reason why I would say it's a dodge is because high concentrations of acid are low pHs, and that can be confusing. So if you just want to avoid the pH scale, you just say it's very acidic. Fair enough.
Less
I
than 2.
perfectly accept that. Okay, if we want to get a little bit more quantified on that, we could then go through and say a pH less than 2. And you pick 2 because, what do you mean acid? The pKa of the carboxylic acid is roughly 2, so we need to be a pH lower than that so that it stays acidic or stays protonated. Okay? So this is what the structure looks like at a pH less than 2. What happens if our buffer balances the pH at a pH of 9? What happens to the structure?
You're gonna lose the hydrogens.
At a pH of 9 was a bad number. Let's pick 10. 9 was too close. Okay, and now your statement is absolutely 100% correct. We would lose the hydrogens on both ends. Our structure was initially what charge?
Positive,
What is it now?
negative.
Does the charge affect its interaction with its environment? Yes. Massively, due to the intermolecular forces. Okay? It's the forces that are predicting what's going on here. So we want a suitable pKa because that is a good buffer. That's what the question kind of states. This makes the pH relevant to the system. Well, why do we care that the pH is relevant to the system? If we change the pH, we change the protonation state, which changes the charge. If the charge changes, all of the intermolecular forces change. Our protein could be completely non-functional with different intermolecular forces. Okay? That's the worst case. Okay? The best case is it just works differently than it does in the natural system. That's problematic because we now aren't studying the natural system. Okay? Make sense?
So when you say suitable pKa, because you want the matching pH, because the charges will change the
Exactly right.
intermolecular forces, which will change and affect the system.
Yep.
And that's what you want, okay.
Okay, so all of these are correct. Our big addition here would be maintain intermolecular forces, maybe. As a nice kind of shorthand for that. Okay. What else do we want?
Choose a buffer that won't interact with the system to, like, interfere with.
So a how do you spell adherence? Pretty sure that's now wrong. Oh well. Non-interference with system. Why?
Because you use the example of the carbonic acid in blood where it could be affected with the CO2 and screw up what you're trying to look at.
If you're trying to study a particular enzyme and how it works, using something that maintains levels, we can't predict anything about how the enzyme works because the enzyme is going to try and change those levels. If we have a buffer in there that is now maintaining those levels, what are we going to observe? Absolutely nothing, because the buffer is preventing those changes. Okay? So we need to make sure that the buffer and system, for lack of a better description there, don't talk. Okay? Because they would then counteract each other. I would say those are the two easiest ones. The other ones I think are a little bit harder, and I think one of them is a repeat of non-interference. They say non-biological. That's the same thing as non-interference. Okay? Non-interference is kind of your grander, overarching thing. The non-biological is a subset within that. Okay? We pick something non-biological because it's not used to seeing that molecule. Therefore, we're minimizing the potential interference. Okay, so I would almost call that two. If you gave me non-interference and non-biological, I probably would not give you full credit because you're telling me two things that are exactly the same. Okay. What else?
Solubility, it has to dissolve and stay dissolved.
Okay. The buffer needs to dissolve. Okay. While at the same time, what?
Not be too much.
The not too much, I would argue, is a separate topic, so we'll come back to that and I'll have to erase some stuff here. If I saturate the system, fully saturate it with buffer, is my enzyme that I'm trying to study going to dissolve? No. So when we're talking about solubility, we need to make sure the buffer dissolves, while at the same time our, we want to call it system or I'm going to go with target. Okay. So we have to make sure that by adding our buffer, we don't mess with the solubility of our enzyme. Okay, the buffer is there to just kind of maintain pH, but it does nothing else. The instant it does something else, we've screwed up our system, and now we can't evaluate our directions, okay, or where we're going with it. Kind of closely tied to solubility is the amount. Okay, and now I'm going to have to erase that top one because I'm out of space. Okay, so we could look at our concentration. Did I spell that right? Gosh. Okay.
You got a Z in there.
Yeah, it does. But it says concentration. So what's relevant in our concentration? And this kind of ties back to solubility. We need enough that we can still buffer a large change in pH, okay, or a large concentration of hydrogen ions being in there. Okay. So we would put a lot in. But as we put a lot in, what happens? We start to conflict with our solubility. Okay. So we need to be careful with the concentration of buffer we use because we don't want that now affecting our solubility properties. Okay. So our enough to buffer, whoops, shouldn't be using blue or red, react with right? Kind of makes sense? Okay. Questions about that one? You'll notice also there's a statement of 2 to 3 sentences at most per choice. Okay. When you look at the keys, typically my keys are written as phrases just because I kind of assume you'll just fill in the paragraphs and make it a sentence. So you should write your explanations in complete sentences. You probably won't lose points for not writing in complete sentences. If you fill the page with text, okay, it becomes exceedingly irritating to grade. So the page or the sentence limit there doesn't mean you need to write 2 to 3 sentences. But if you get the gist of it down shorter than that, great, that's ideal. The only reason I say 2 to 3 sentences at most is every semester I get somebody writing me 2 pages for a single one of these. I'm like, I don't want to read that. Okay? The point is short to the point answers. That's what you should be focusing on. All of them. Very, very rare I ever ask a question that is worth opening up into pages of text. Okay. Questions on that one?